Okay, I think we can probably start. Okay, so thank you for coming all. So this will be December presentation of Link Tech Talks, and I'm very happy to have here Francisco Forster Buron, especially because today I realized that it's holiday in Chile, but he very gratefully came here, also with the engineering team, so we can also discuss technical questions about ALeRCE broker. So Francisco got his PhD from University of Oxford in 2008. He is a researcher at the Millennium Institute for Astrophysics and also researcher at the Center for Mathematical Modeling, as well as the full professor at University of Chile. He is mostly interested in astroinformatics and supernova science, and he was a principal investigator on the High Cadence Transit Survey, and he's a lead on the ALeRCE broker, and I'm very excited to hear more about that project. Okay, so Francisco, take it away.
Thank you very much. I'll share my screen. Okay, so can you see my full screen?
Wonderful, great, yes.
Okay. Okay, so thank you again for the invitation, and thank you for coming for this talk. I will talk a little bit about the ALeRCE broker, the different tools and services that we are providing, the experience that we have gained building this tool, which is really an interdisciplinary project which involves many institutions in Chile and also some in the US. So in ALeRCE, basically, it's a large collaboration that is divided in three main groups: the astronomy group, machine learning group, and infrastructure group, with a lot of overlap between them. But this is the basic way we work. And the main funding institutions are the Center for Mathematical Modeling, the Millennium Institute of Astrophysics, Data Observatory, and the University of Concepcion. Okay, so I will show you some slides that you may all have seen. So the motivation for this work is this new generation of optical surveys with large ATEN-views and large CCD cameras. So in here you see field of view versus collecting area. The circle size is the ATEN-view, the product of the two, and LSST, Vera Rubin Observatory, is really going to change this field because of the large volumes of the universe that is going to be able to observe. And I took this figure from this website. You can see some key numbers: huge camera, amazing cadence for the size of the telescope, many billions of tens of billions of objects, and lots of data that is going to be collected every night. And in terms of brokers, of course, we are interested in the ALeRCE stream, and we looking at this document, you can see the composition more or less of the ALeRCE stream. For every visit in the ALeRCE stream of LSST, there will be about 7,000 variable stars detected, changing with respect to a reference. About 3,000 solar system objects, about 200 supernova, active supernova, about 70 active AGN, and up to 500 bobos, if you look at the purity of the stream. So this is a huge challenge. There will be very large bursts of alerts every time, for example, the telescope is visiting the Milky Way. You will get up to 40,000 of these objects in one shot. So this is a huge challenge, but a big opportunity also. So because of this, there is a new kind of element in this ecosystem of time domain, where you have first the survey telescopes that are looking for changes in the sky from the ground, from the space, in different wavelengths and messengers. And these telescopes will be detecting changes, and we'll be reporting them in streams that will be processed in part by community brokers. In particular, in the case of Vera Rubin, there are 7 community brokers that are listed here, and they will likely be ingesting data from other sources as well. And there are other projects as well that are going to be trying to do the same. These brokers will feed, in turn, other brokers, so the brokers of brokers, and the target observation managers that will link the classifications, the prioritizations with the telescopes that will do the follow-up. So then there's the follow-up layer where you will really characterize the most interesting objects. If there is a requisite of observing fast, you may be able to do that. And of course, you can also feed this information to the user community for them to do post-processing or real-time analysis. So as I said, there was in 2019, there was a call for letters of intent to become community brokers. We sent one of these, and after a process that lasted about 2 years, there were 7 brokers selected. ALeRCE is one of them, and 2 downstream brokers. And you can see more information on this page. So the first question that is asked a lot when we talk about ALeRCE is, why do we need more than one broker? And to me, the answer is very clear. I mean, we need diversity. Otherwise, we are risking to stagnation. And we know that in technology, we have this winner-takes-all type of solution that I think we should avoid. And why? Because if you want to test, bring new ideas into production, it's easier for smaller teams to try them and move faster. And so instead, we can work together in standards and benchmarks, tutorials, workshops, involve the user community. So in my view, a broker is like building another instrument. So you can have many instruments doing similar science, and you only need only one. So what do brokers do? Well, the answer is not very clear, and I think the current landscape is being defined by the broker teams. But one of the things that we have seen that are probably necessary, the minimal things are, for example, to provide a stream of annotated alerts. This could include filtering, classification, adding features, cross-matches, etc. And then you can start adding things. For example, you can offer cross-matches with different levels of detail. You can offer web interfaces or a client or APIs or access to a database. You can offer filtering services. So for example, you put certain criteria and the string is filtered automatically according to that criteria. Or you can classify according to a given taxonomy, which is the approach that ALeRCE is following now. You can also compute features that fit the classifiers, but are also useful in their own sake. And you can provide watch lists. Watch lists are lists of positions in the sky that are trigger notifications every time there is an alert close to one of the positions that you ask the system. You can connect with follow-up resources. You can add multiple streams of alerts, not just Rubin, of course. It's CDF with 2A, Atlas, LSST, and then there's also LIGO, Virgo, IceCube, etc., with different messengers. You can try to detect outliers, which may be perhaps the most interesting thing that will come out of LSST. You can provide regular data releases. And of course, you want to make everything as reproducible as possible. So there may be more elements in this list, but I will not go into the detail of all of them. I will just focus on some of the things that we are doing, and we can discuss later. So let's talk now about ALeRCE. What are the main scientific questions that we want to answer? Is basically answer these 4 types of questions: transients, what are the progenitors, the explosion physics. Then this connects to cosmology, variable stars, different types of variability. This is connected to also the distribution of matter in the galaxy, AGN, the different ways of variability in AGNs, how we can use them for other things, and the connection with transients in the tidal disruption events. And of course, it's solar system objects. And they are in the stream, and we can also do science with them. But the main driver is really the first 3 in this list. Okay, so how does ALeRCE work? Basically, ALeRCE has a pipeline that we have built through a lot of trial and error that is based on Dockerized steps that are shown here. So as in the case of CDF, we get the stream, and actually this is a bit out of date. There's one step I did not include here. There is actually you get the alert, and you first assign a new ID in the case of when you have multiple streams, and then with this you start doing processes like cross-matching and uploading to AWS in this case, and then trigger different classifiers: image classifier, the stamp classifier, and the light curve classifier and outlier detector in the case of ALeRCE. And this generates a new string of annotated alerts. We have tested this system. Of course, you can change the speed at which this works depending on the infrastructure that you use. But we have tested this system, and we can get to times of less than 1 second execution time per alert, including all the steps shown here. And since the arrival of the alert to the emission of the new alert in less than 10 seconds or a few tens of seconds, including all the steps. So we use Kubernetes and Docker in here, and we monitor everything using Grafana. The core of ALeRCE then is our 2 classifiers. So as I said before, we do classification based on taxonomies. And these 2 classifiers are the stamp-based classifier that uses a convolutional neural network with a simple taxonomy, because you only have used the first image stamp to do this: AGN, supernova, variable star, asteroid, and bogus. And then as we get more data, and we can build a light curve, and if we have at least 6 points in one of the bands, we can trigger this light curve-based classifier. That is, in this case, is a balanced hierarchical random forest that has 15 classes that are shown here. And this is the confusion matrix. This is evolving. There's new tools, new technologies, and well, later I will discuss what is probably the next step. Also, we have built many web interfaces. Here is the ALeRCE Explorer, where you can quickly search for your favorite class of objects, and you can visualize them. You can see the light curves, some basic statistics, machine learning probabilities, the image stamps, the contextual information using allowing light, cross-match information as well, using CATS HTM. So building on what the community has already built and adding the information that we have. And you can quickly switch between objects in the ALeRCE Explorer. Then we also have the Supernova Hunter. This is basically help us find the latest supernova, and that shows you just the best supernova candidates, the best 100 or the number that you want, and you can quickly explore them and provide feedback to the system, so that an expert team can look at them and then submit the candidates to the transient name server, and this allows for fast follow-up. It's also the watch list, where you can, as I said before, you upload a list of objects that is explained there, and then every time there is a new alert that matches the position, you get a notification, and you can go and see the new point in the light curve using the ALeRCE Explorer. So all these tools are connected using a single user, let's say, authentication system. We also have part of the classification involves the creation of many features, the computation of many features, in total 174 features. So this sounds like exaggeration, but really makes a difference. And why do you need so many features? Because you have really so many different classes in our taxonomy, from persistent variable objects to transient objects to periodic objects. So different classes need different features. And in fact, these are the top 5 most important features for the different classifiers. So our classifier, the light curve classifier, is hierarchical. So it has first classifier that classify things into transient, periodic, or stochastic. These are the most important features. So colors in Ys, something related to the star or galaxy, the fraction of positive values, and some parameters related to transients. In the case of transients, almost all the parameters are related to fits to the light curve using a parametric model that is a modification of the Villar et al. Parameters. And in the case of stochastics, wise colors again, and many different colors. In the case of periodics, of course, the period and colors. This is what we see. Something else we do is we integrate the data releases into the alert stream, so we can see both the alert information and the data release. And this really gives you a completely different picture for some objects. Like in this case, if you see this from the alert stream, you don't really realize that there's something else happening, and you can see that in the data release. And this is critical for looking for outliers in the case of persistent sources. Something new that we have developed is a method. If you have transients and you want to classify them well, you may want to know the distance. And to know the distance, you may need to know the host galaxy. But it's not so easy always to identify correctly the host galaxy. So inspiring in how the animal vision system works, where you have higher resolution in the center of the visual system, we build this classifier that uses a hierarchical representation of an image that is fed into a neural network, convolutional neural network, and this predicts the most likely position of the host. You can install this very easily and really works wonderfully. This is an example of how we report candidates now using Delight. So you see a list of candidates, and the position of the host is automatically identified by Delight. In this case here, you will see a point. So there, sometimes there is no matches, so it also reports no matches, and really works really well. And this information is sent to the transient server, so people know the redshift of the transient candidates every day. So then another problem that is going to be more common is satellite contamination. And this is something I discussed before in previous conferences, and we have started tackling this more seriously. So if you look at the image stamps of CDF, they have a decent size, but if you compare them to the image stamp size of LSC, they really look tiny. And there is many examples of satellite glints, which is like a satellite that is leaving a string of pearls in the sky. If you have a very small image stamp, you will not see it. So somehow we need the larger scales in the image stamps to do good classification based on the images. And for this, we propose hierarchical representation of the image stamps. And so we said this some time ago, and actually we're working on a publication now that basically shows that if you don't do this multi-resolution representation of the image stamps, many satellites will be confused with supernova. You need these larger scales in order to really separate the satellites from the supernova. And this is something that we are about to publish, and hopefully somehow convince the LSST team to take this into account. I know this is a huge change, but I think it's worth it. And then coming soon, I will not give many details, just give you the preview of, you may know that there is a current challenge happening now. It's called ELASTIC. That is challenge of classifying the alert stream of simulated LSST in the future. And we are part of this challenge. And we will soon explain how we got this amazing coefficient matrix. I will not give details now, just give you a preview. And this is called ATAT, this new classifier. So, and the author is Nicolas Astorga. Well, so all these classifiers have allowed us to influence, let's say, a community of users to use these resources and for their science. And in fact, we have users in many countries around the world, and we are we're among the top 2 groups that have published more transient candidates to DNS and the transits that are classified were the top 3. So you can follow all the confirmations of candidates reported by ALeRCE in this Twitter feed, and you can see the classes of objects that we report that have been classified the most. So there are many also TDs recently. So how do we allow the users to use ALeRCE? We provide an API, and you can access here using the Open API protocol. It's all well documented to access the alert stream and all the enriched features and statistics and probabilities that we compute, and also the data release of CDF, so you can play with it too. And also there is a client that uses the API that works in Python. It's very easy to use. We also provide direct access to the database. So this is an example of how you query things in the client, but you can do more sophisticated queries, including inner joins and things complicated, through direct database access. If you want to do this, you have to contact us, because we, by default, will limit the time or the maximum time of these queries. But of course, if you want to do some complicated queries, you can ask us, and we can provide you some better access. So how's the database in ALeRCE organized? Well, we're in a transition. So today, ALeRCE uses PostgreSQL system database engine. This is what is in production. In parallel, we have switched to MongoDB, which is the database used by CDF that is in staging. And in here, we have data from CDF and from Atlas. In the case of Postgre, this is the way the database is organized. So we have the more, atomic data is everything that is time dependent. So everything that is in Lightcode points or non-detections, or everything related to the observation. These are time dependent variables. These are in these 3 tables. Then we have things that are not time dependent, but that they depend on the filter. So statistics of the Lightcodes per band, or features that are computed per band, or this is about the reference image used to generate that image difference. And then there is a non-time dependent and non-filter dependent tables, like the object, which includes basic statistics and crossmatch. And here are some numbers from the last time I computed this. So as I said, we are moving from Postgre to Mongo. And the idea is to first use Atlas as a stepping stone to get to Rubin. So because the number of alerts that we are generating for Atlas are of the order of 1 or 2 million per night. So it's really more challenging than CDF. And in the future, with Rubin, we know that we need a distributed data system, a database, sorry, because just the number is so huge that we will need something different. So we are putting our bets on NoSQL like MongoDB, but this may change. So Nevan asked me to list some engineering challenges that we have encountered in the project, and I put here some. So first is communication between astronomers, machine learning experts, and engineering team. This is very important. So in ALeRCE, we have many meetings, but short meetings in general. So perhaps more than we need, but we want to ensure that we communicate well. So we have the engineering team meets daily using agile methodologies, and the astronomy and machine learning teams meet weekly. But they are also they also participate sometimes in the engineering teams meetings. Then, in terms of our pipeline, the maintenance and monitoring of the pipeline is is really a lot of work. To operate the pipeline, we use Kubernetes and Docker, as I said before, and we use Grafana to monitor. And a lot of effort and time has been put into improving the Grafana dashboards, including the execution times, the classifications, the number of alerts that are arriving, that are being sent, etc. Also, maintaining the APIs has turned out to be a bit of a nightmare. Because there are so many, and for this, the engineering team is using Kubernetes also to distribute the load, and then of course maintaining the Python client and the web interfaces. So the web interfaces have also changed, especially when we add Atlas data. So the fact that we are able to be able to show data from two different sources that are very different requires many changes in the interfaces. So a problem that I think is still in progress is how to maintain and design the database that is flexible enough to include these new changes in the data, but it's also scalable enough. Since this is perhaps the biggest question to me. We are betting on Mongo, but yeah, let's see what will happen with Atlas. With Atlas, we're learning a lot about this. Also, identifying use cases, relevant use cases that guide the database design, and also how to continuously adapt, something I mentioned before, to new sources of data. So we are started with CDF, then we include Atlas. It was much slower than we thought to make the two talk to each other, and then we have to do this again with Ruby. So, and this will be harder. So these are just some of the challenges we can discuss in the time for questions. And how we envision the future infrastructure, we envision 3 layers. So the online processing layer, where you have the Kafka regulating the different streams, getting metrics and regulated by Kubernetes. Then a post-processing layer that you need to train new models, to compute features, to ask difficult questions to the data. And then serving layer to let users get into the system and do more complicated, complex queries as well. So I'm not sure I mentioned, but we are currently running in AWS, and we have got a new system, a new server that is like 5 different computing nodes, 2 database nodes, and 1 GPU node for Ruby. We tested our system at the level of LSST, and we can do, in principle, what we want in the future. We are not running with this level of infrastructure, but we know it's possible to do. And then how we can contribute to Link. So I enter the Link website and I look at some of the points here. So you said that you want to fulfill some LSST scientific goals, for example, building upon data to solve problems like identifying which transits are exploding, obtaining distances for cosmology, locating and tracking moving objects. And I think the Lightcode classifier can help with this problem. The stamp classifier can help with this problem. The light, the identification of hosts, can help with the distances. And the stamp classifier can also help with tracking moving objects, because we can classify solar system candidate objects. Then helping the LSST user community prepare, sharing end-to-end analysis to make them reproducible. We have many use case notebooks that are all public. You can check. I think we have the same idea of making them reproducible and personalizable. Enabling access by a larger community. I think the APIs are key here, having the client APIs, so that you don't have to be living inside an external system to do your science. In LSST, you will have to probably do both, because sometimes you want to be close to the data, but for simple queries, APIs are useful. Encourage engagement, etc. And I think this talk and I don't know, future collaborations between the two groups. Then training the next generation of scientific leaders. Again, I think use case notebook and examples of how to use these tools. Workshops, we have organized and co-organized workshops that you can find in this website. And yes, why not exchange student postdocs, engineers, and get the sparks out of this. So this is the end of the slide part of my talk. So you can see here some websites, the main page, the Explorer, Supernova Hunter, watchlist, use case notebooks, workshops, and the main publications, the presentation paper, the stamp classifier, the LightCube classifier, and also include here an anomaly detection in the case of agents.
Okay,
so,
Francisco. Sorry.
Yeah.
I suggest we do questions now a little bit, and then we can go to notebooks, especially because the chat is not available, and that's my mistake. We were playing with Post, and by default from October, it seems that it's disabled. So that's my mistake. All right,
by the way, I'm looking at also the link Tech Talk channel in the LSSTC.
That would be lovely, exactly. So I would suggest if you want to ask a question, either raise hand in Zoom or just unmute, or ask a question in the Slack. Okay. So maybe Andy, we can start with you.
Thanks, Francisco. This is really lovely talk, really fascinating stuff. One thing I was wondering about, I'll turn my camera on, sorry. One thing I was wondering about was, are you thinking about visualization and how visualization might actually work when you start going to, I'm just looking at your notebooks and things like that, and you're looking at your different examples. Are you thinking about visualization and how it might work when you're really starting going up to a much larger scale with Rubin, and what sort of ways you might interact with data?
Yeah, we look at that at the beginning. The first web interface that we had, you could visualize the distribution of objects that you got after a query, and we were using Data Shader, which is a really cool tool. But that was brought us lots of problems at that time. I personally, I think that's a really important problem. But we have so many other problems now that we need to collaborate to really solve this problem. We're not putting a lot of effort now, only on the web interfaces, on how to look at individual objects. I would say this is what we are doing now. But definitely with Data Shader and circling with your mouse and do some interactive things, this would be great. And yeah, when you're talking about billions of objects, there's no other way. Yeah.
I have, unfortunately, many questions. I see Drew is typing. One of the questions which I had, really, LSST stamps are so small compared to ZTF? Is that what like the broker is giving out? Because obviously the field of view is huge, but what it's decided, or how does that work?
Yes, because the pixel size is smaller. So ZTF's pixel scale is 1 arcsecond, and LSST is 0.2, I think, 0.2, I don't remember now.
Right.
Yeah. So
you get only one chip, right?
Yeah, in arcseconds it's tiny, and I think it's too small. This is my feeling, because if you want to look at you want to see the galaxy and be able to do fast classification of a supernova, this may be too small.
Yeah. Eric, were you? Sorry, Eric, were you thinking of saying something?
Nothing important. I mean, the Rubin field is smaller than the ZTF field, of course, but yeah, Francisco's made all the right points here about pixel scale and data volume. So yeah, it's just a constraint of bandwidth to get the pixels out, and the hierarchical scheme that Francisco's proposed is very interesting, and I think it's we need to see if that's something that we can convince the broader community is the viable way forward.
Yeah, and the thing is that, I mean, the image stamps are not really used to do science. They're used to make some fast decision about something. This is really the main use case. If you want to do the science, you will go to the image and then do some processing. So when the comparison that we are publishing, we did a fair comparison of using the same number of bytes to process the images. So we're not asking to use more bytes per image stamp.
Okay, Francisco, so I see from Drew, who is one of our engineers here, links. So he's asked, so do you anticipate reanalysis of data persist in the database? If so, how do you anticipate maintaining historical data and identifying the most recent data in the database?
Okay, different versions of data releases, something like this.
Right, but I could imagine, let's say that you want to reanalyze the data and you had a different, maybe, different version of the pipeline which analyzed it or something like that,
Yeah, so at the moment we are being very careful of adding a column with the version of which data was used, which feature structure was used, which classifier version was used. And there's a system of dependencies that is kind of implicit, is written down, but we in principle we should be able to track down which data was used with which version of everything. And we haven't counted this many times because we have to recompute everything from scratch many times in CDF. Yeah, but it's when the data volume is so large, it starts to become more difficult. Yeah.
And maybe I can ask regarding the data volume. You had all of these 150 features, and they were separated in different periods and different. What are they used for? But you compute that on every light curve, right? It's not that you determine this is stochastic, and I mean that seems also quite big. Like, how is that done?
We do it in every light curve with at least 6 detections in one band, which makes the number of objects to be computed much less than the original ALeRCE. So it's like from 200 million to a couple of millions. Okay, but anyway, when we designed this new server that we put for LSST, the main bottleneck, the main driving force for the design was feature computation. In the end, we may not need the features. Who knows? But we assume that we will. Yeah.
Okay. Any more questions at this stage before we look at the demo?
I had a couple. The first was following up on the feature computation. I was curious, Francisco, what you've learned. I mean, I saw the paper is coming, but what you've learned so far from the elastic simulations, where you have a sparser cadence, more filters, and how that's been going.
Yeah, I don't want to read too many details, but yeah, we had to redefine all the features, especially for the transients, and it turned out to be really important to recompute them in a different way. And it turned out to be like one of the most important features to really take into account all the bands. But there are models that don't use features and do really well. So
we'll look forward to seeing that paper then, for sure. The other question I had was, in the past you talked about looking at Cassandra as your data store in the ALeRCE era, but now you're seems like you're talking more about Mongo, and I'm curious what drove that decision.
Basically, I would say it's like looking at CDF. CDF was using Mongo, said we had different options. I know that Ken Smith has done many tests on Cassandra, so we said, okay, let's try testing Mongo. But yeah, if the community moves to Cassandra, we may also do that. Yeah, I'm not so sure about if we will be able to do the same type of queries that we do now. Sometimes complex queries that take a long time. This will take longer or a lot more infrastructure to answer. So yeah, I think we need really a community effort to answer this particular question of which database to use. It's a very large problem. I don't know what is the current feeling you have.
I don't feel like I have any, expert knowledge here other than, certainly within ZTF, there's a pretty steep learning curve to query Mongo effectively. It's the query language is quite unusual, and that's been a hurdle for sure.
Mm-hmm. Yeah.
Okay. If that was all, Eric, or others. Oh yeah, let's go to demos now for maybe 10 minutes, and then we'll have another maybe 10 minutes for discussion about the demos or the previous, or everything that's available.
Okay. Yeah, so I think some of you may have seen this, but I will show anyways the ALeRCE Explorer. This is ALeRCE Explorer. So here you have a search area where you, for example, select a given classifier. So the light curve classifier and a given class, let's say type 2 supernova, which is my favorite type of object. Then I search and I see the highest probability here objects, and I can click. And as I said before, you see the light curve. I can click at any point in the light curve, and if there is an image stamp associated, because not all points have image stamps, you will see it. You see the classification, and you can move between objects. So let's go back and query a different type of object, ALeRCE stars, for example. And here I see the top probability objects, and here is the light curve without folding and with the folding.
And Francisco, the highest probability that is that class that you're claiming that it's that class, right?
Yes.
That's what it means.
According to our classifier.
Mm-hmm.
Yeah. So another case example. Another example. And yeah, so you can see in the source in Alloy Light. In the case of, let's look at blazars, for example. We have AGN, blazar, and quasar. We have these three classes. Again, we can see the light curve. And something interesting is that you can display the data list like information. So you can see the G, R, and I bands in the data release. You can also turn them off, and you can see the light curve from the alert stream. And you can see also if there is cross matches. No, I don't think in this object, but you can see cross matches at the bottom. Yeah, okay, so that's the ALeRCE Explorer. Now I will start the quick notebook that will run in Colab to show you how the client works. You can also use this link. So this is something that we prepared for the ADAS recent conference recently. So I will run, get some libraries, and I will install the ALeRCE client. And then I can import it. And I can initialize. And these are the different things that you can do with the client that are listed here. So let's start with, for example, doing the simplest of all, just querying one object. In this case, a supernova, CDF 20AAE Lulu, it's type 1C supernova. And you get this information, the time of the first observations, the G minus R at maximum, the coordinates, etc. And actually, these are all the columns that are available, and the explanation are in here. Now let's query the statistics per band of the same object. You can see for filter ID 1 and 2, which is G and R bands in the CDF. You can see the mean, the median, the maximum, the minimum, etc. And I'll explain here. And these are the columns. Let's now query the detections. So here was query objects, then query max stats, then query detections and query non-detections for that object. And now we get this bigger table with detection, the properties at every time that the object was detected. And now we have a telescope ID column that we will populate with CDF or Atlas. or LST or whatever. And here we have more information. We have the candidate ID, the filter ID, and whether it has a stamp associated, whether it was corrected, because we believe it should have been corrected with the reference image. And here you see the correction steps, the IDs, so you can see the version control. And yes, and many other properties. And the non-detections, it's more simple, is the time, the filter ID, and the limiting magnitude. And of course, you can plot this, and I will not do this now. Query the image stamps. You can do get stamps with the object ID and a given candidate ID. So for example, the first candidate ID in the detections table, and we got them in this object, which are fits images. I can plot them. And here are the three images, the science, reference, and difference. So this was a supernova, and this is a quite large galaxy. You only see the center here. You can also plot them directly in here. And you can see that in this case we use the first detection, but by default it uses the last one. So this shows you the last detection. We can also cross-match with catalogs in the vicinity. We are using the CATS HTM, and for this you do CATS HTM consearch, and I selected a few catalogs, and then I get an object with all the cross matches and with information provided by each catalog with its own peculiarities, etc. So I can plot just quickly the position of all the sources, so many Gaia sources, the object, and then the spec Sloan and net set. So I have the redshift probably of the galaxy. I can also query features. So for this, I use query features. And I always, as you can see, I'm outputting everything in pandas format because it's just what I like. You can also do VO table if you like it. And we get a more complicated thing now. So we get the name of the feature, the value of the feature, some ID of the band that was used. So 0 is not related to the light curve. 1 is band G, 2 is band R, 1, 2 is like I use both bands. And this is the version of the feature computer. So it's 178 rows. And you can do the pivot routine in pandas to move this and transform this into columns. It's explaining other notebooks in the use case notebooks. So not is here, sorry, it's here. So I can transform this into amplitude in the filter ID 1, amplitude in filter ID 2, and so on and so on and so on. So you can access the features for any object in CDF. It's already computed by ALeRCE, and you can access very easily. Then query the probabilities according to our machine learning models. As I said, there are many machine learning models. It's the stamp classifier, the light curve-based classifier, and all the hierarchies within the light curve-based classifier. So to do this with query probabilities, and for just one object, we got 37 rows. Why so many rows? Because for every classifier, we get one row per class in the taxonomy. So we have the probability for the given class according to that classifier and that version of the classifier. And we get a column that is called ranking that tells you which one is the most likely class according to that classifier. And this ranking column, that is something that you may think that why did you include this? Actually, it's very important because normally you're only interested in the top one class. So if you have this column and you index this column, you can very quickly ask for the typical questions that you may need to ask. And if you also want to know the other class probabilities, you can also access them. And in fact, Elastic, in the end, they are doing something very similar in how they report the probabilities. And actually, you can look at all the unique classifier names are hierarchical random forests. Is the version. This is the version, and this is the name. So it's the light code classifier, the periodic branch, the stochastic branch, the top layer, the transient branch, and the stamp classifier. These are all the classifiers, and these are all the classes within each classifier. So the light code classifier has 15 classes. The periodic, only the periodic classes. Stochastic, only the stochastic classes. The top, the 3 main branches. Transient, the supernova classes that we include. And then the stamp classifier, which has the 5 classes that I mentioned before. This is all explained in these 2 papers, Sanchez-Saez 2021 and Carrasco-Davis 2021. So now let's query some global properties. So, and for a set of objects. So here I can do query objects and give me all the type 1a supernova according to the light code classifier with a limit of 200, ordered by probability in a descending order. So you can quickly get these results. And these are the top 200 type 1a supernova. This is used by the web interface to show you the results. It's using the API all the time. So you get 1 row per object in this case with the basic statistics for this object. And then I can also say, okay, now give me type 1a supernova that have a ranking of 1 or 2 or 3. So objects whose second most likely class is type 1a supernova and whose third most likely class is type 1a supernova, and so on. And I will plot the distribution of probabilities. And you see that if I don't specify the ranking, just by default, it will use ranking 1, which is basically overlapping the light blue and red, and they have probabilities larger than 0.5. And the things that have a probability that is the second most likely class is below 0.5, and third most likely class is much lower. So yeah, so you can explore sets of objects as well. And finally, this is a way to create a link. So you can go and use in the Explorer, look at all these objects. So this kind of interaction between the notebooks and the Explorer, and I can very easily explore them and see, okay, yes, this makes sense. These are type 1a supernova. And with this, I stop because we have 5 more minutes.
Okay, let's have more questions. I could ask, I'm wondering, when you have these stamp images, which are really nice, how will that work in LSST era? Will you have to instantiate Butler in order to pool this data stamp, or how does that work?
I mean, they will come in the stream.
In the stream, they will come. Okay, yeah. Right, these small stamps. Okay.
Yeah, I think also, I mean, perhaps if you have more technical questions, there is also many members of the engineering team. You may want to ask them about, I don't know, Kubernetes or I don't know, perhaps Diego, do you want to say something, Ignacio?
I can say something if there's a question.
Okay, Warren, please go ahead.
Oh, thanks very much. Thanks, Francisco. I'm coming from a perspective of observatory operations, an observatory that would be used for follow-up of some kind of transient object. You know, I work for TMT,
Yeah.
so about the operations planning for that. But it's relevant for you know, the 8 and 10 meter class telescopes at the moment, that sort of thing. And you'll have to forgive me, you know, if I've sort of missed some of your points. Can a user define a set of criteria to generate an alert stream that comes out of ALeRCE, and that alert stream could be used to sort of automatically trigger a target of opportunity program on a highly automated telescope? Could I see how you can do lots of analysis and things of information that's in ALeRCE, but in terms of amalgamating all these incoming streams from ZTF and space facilities, for example, that sort of thing, processing them and generating a refined list of alerts. Is that something which is really an aim for ALeRCE?
So we are working with a different philosophy of providing you with a classification taxonomy and probabilities. So, for example, the alternative view is what you're saying, like I define the filters, I define the criteria, and I do like cut in a plane, and then I select these objects here. But we are using a different philosophy, which is we have a taxonomy, and machine learning will tell us the most likely class according to this taxonomy. And then you can filter within the most likely objects of the given class. But if you do this like more like, let's say, manual criteria of cutting here and here and here, it's like going back to the traditional way of working. And we're not using the machine learning. But yeah, let's see how this evolves. But I think there's very different philosophies in working. And if the community really needs this, we could somehow mix the two.
I can add something related to that. So most of our users access our database through the API or the client or whatever, but some of our users can access the full stream, like in real time. For example, now in Elastic, we are submitting the whole output stream with all the classifications and stuff back to the people of Elastic. And in the future, or if someone is interested, we could stream in real time our whole classification stream back to someone to do further analysis. And for example, taking the classification products and making some decisions over that instead of some basic properties.
And there is already a classification stream. It's public, but you have to actually request access, but we won't deny access. So it's public, but not really public.
Okay, thanks very much. Yeah.
Okay, Nat, please.
Yes. Thanks, Francisco. Just to follow up on Warren's question, I mean, so one of your first slides, you had the connection to things like TOMs, right? So I suppose that someone who had time approved on a follow-up telescope, they could create a list of targets from using your filters and of things that are probable objects that they'd be interested in, feed it into a TOM, and that would go and schedule an observation. So how I guess complete is that ALeRCE and TOM interface at the moment? I mean, could somebody actually, schedule an observation through a TOM using a set of objects that they had defined from ALeRCE?
Yes, actually, the TOM developed by the TOM toolkit is listening to the ALeRCE stream. So the supernova candidates are fed into the system, and then someone can select a particular object and automatically follow up. But yeah, so we think that there are different types of follow-ups. If you want to do like 8-meter class telescope or very large telescope, you want to look at the data. You will not do it completely blind. And if there is many small telescopes, robotic telescopes, you may want to do this more automatically. And yeah, so we're using the philosophy of trusting the taxonomy, because we know that if you want to classify something early, machine learning does it better than what we can do. This is what we're seeing. Yeah, it's difficult to know because there are so many variables. Yeah.
But if your science case depends on very rapid follow-up, for instance, before the object fades away, then you may not have very much time to look at the data. And I mean, if somebody proposed for the telescope time to say, I'm going to get a steady stream of candidates from ALeRCE, and we are automatically going to schedule follow-up with them in order to catch the ones that are really interesting, then I mean, a TAC could evaluate the probability of success of such a program.
Yeah, for the very fast objects, the best thing to do is to use the stamp classifier, because you only need one detection. And there's very little you can tell about the light curve with only one detection. So yeah, so that's the balance there. So if you look at TNF, we are reporting earlier than other groups because we can use the first detection only. And then the filter is a few hundred objects per day. And then you can basically use the API to do second filtering. Yeah.
Okay, last comment by Rachel.
Hi, everybody. Thank you. Just to follow up on Knut's comments and Francisco's response, there's kind of a secondary loop. The ALeRCE API enables everybody to pull from the stream whatever they are personally interested in. And the TOM toolkit does support doing that programmatically, but you can always implement a second stage of filtering within the TOM itself to say, okay, I'm going to ask for preliminary observations, say a spectrum, just to check this thing is what I think it is. And then once those data are in and you can assess those, then maybe you trigger the follow-up from the larger aperture facilities. So there's another step that can be in there to maybe make the most out of the large aperture time.
Okay, Alex, do you want to give last comment or?
Yeah, sorry. I mean, I'm sorry if I overstated my welcome. I'm Alex, engineering team from ALeRCE. So I just wanted to say very fast that this is a use case that we as ALeRCE team had considered, but to me, as I hear the discussion, is getting very interesting that we may, if the necessity lays in the community, work in this new kind of approach. It's very important that we don't let science over the table.
Okay, wonderful. Thank you. We are just over an hour. And what a great follow-up, because the next talk will be in February. It will be about TOM Toolkit. The January talk slot would have been January 12th, which is heavily conflicting with AAS happening in Seattle. So we were looking at alternatives, but on the end, we will cancel the January talk. And then the next one will be in February, and very likely it will be TOM Toolkit, exactly. Okay, lovely. Thank you once again, Francisco. What a lovely talk.
Can I say one more thing?
Yes, of course, please.
Yeah, but we are interested in organizing a conference on brokers next year. So if anyone is interested, please write to me and perhaps we can do something together.
Wonderful, great. Okay, this was lovely, and I think we'll have a lot to talk about and write about. Okay, wonderful. Thank you once again, all.
Bye. Thank you.
Thank you.